All right, let's go and talk about homework 19. How's the phase diagram of most substance differ from water? What's the big difference? Of slope is negative for the solid liquid phase change. So you end up having increases in pressure that melt solid water. All the other substances, when you increase the, well, not all the other substances, but for all practical purposes, all the other substances, when you increase pressure on them, the molecules get closer together and they become a solid. But with water, you increase the pressure and you liquefy it. So it's a serious difference with the phase. Okay, let's throw a phase diagram up here. So I'll go with I'll go with pressure here and temperature here, and then something like, are we doing water? Mm-hmm. Okay. Something like that. And we've got solid and a liquid and a gas. And we probably want to, let's say, put a dot right there and a dot right there. And we'll call it critical temperature. So that's that one, and then triple point. That one right there. So what's the critical temperature? What's the significance of it?
Where it never forms a liquid?
Correct. So once you've reached the critical temperature, when you're measuring something's temperature, technically you're measuring what? Its speed. So what we're talking about is molecules that are at a high temperature, which means they're moving so fast that even if you squish them at incredibly high pressure, you still can't liquefy them, because to get them to turn into a liquid, they have to like touch each other and come in contact. They're simply moving too fast to form an interaction with each other. So once you've reached that critical temperature, you can't liquefy something no matter how much you squish it. And that triple point, it's a strange anomaly of what's happening there. Everything, all phases are happening there. You're seeing solid, liquid, and gas. You're seeing boiling and condensing. You're seeing evaporation, and you're seeing melting and freezing and deposition and sublimation all happening at the same time. Okay, and then the last part of this we'll do, so melt, freeze, and sublime, and deposit, and vaporization, and condensation. Okay, I think that's probably it for that. So how about this one about water's temperature? 4. Okay. So 4 degrees Celsius, water's most dense. And what happens when you raise or lower the temp? So what happens to its density? Density decreases if I raise or lower the temperature, which again is very, very weird. Explain why your ears hurt when you dive down into a swimming pool.
Is the weight of the water in your body?
Weight of the water? Nope.
The pressure?
Okay, well, so more than just that.
Your body's trying to equalize pressure.
Well, what's the pressure from the water due to?
It's the interior and exterior pushing in on each other.
Where do you get that external pressure that's pushing? What's that come from?
It's from the density of the water.
No.
Nitrogen in your blood.
No. What's pressure from? We talked about it last time. To exert a pressure on something, what has to happen? Over area. Force over area, right? So the deeper you go, the molecules, what's happening to the molecules that are exerting the force?
Well, there's more.
There's more of them. That's it. So if somebody's doing this thing to your chest with their index finger, right, hurts. What if you have 10 people doing that? More pressure, right? Somebody sets, I don't know, a brick on your chest. Not a big deal, right? What if they put 10 bricks on your chest? More of a big deal, right? So it's more things impacting. So the deeper you go down into the swimming pool, there's more water your eardrum is simply getting hit more often. You're getting pounded by more of it. All right. So we want to react zinc metal and hydrochloric acid. Okay. So I'll put zinc here and I'll put hydrochloric acid here. What do you get when you react those two things? You get hydrogen gas and you get zinc chloride. And so the state here is aqueous, the state here is solid, the state here is gas, and the state here is, why is that last one aqueous? Because chlorides are soluble, there's no zinc rule, and there's water present, and there's water present because the hydrochloric acid is aqueous. So I already had water there in the first place. Balancing this.
Can I ask you a question?
Sure.
Yeah, I can't remember what the last equation was that we had hydrochloric acid and we all thought it was aqueous and it was a gas.
It was a product.
Oh, when it was a product?
Yeah. So
Oh, because it
just
started out with gases?
just think about, it doesn't matter what I started off with, just think about what's going on here. This person is going to react zinc metal and hydrochloric acid. So your two options for an acid are a gas or have it dissolved in water, so aqueous. So if you're going to take zinc, you guys absolutely did this already. Last week when you put the zinc in the hydrochloric acid, that was the one when you put the match in and it whistled. So you did that. Would it make sense for you to do that with gaseous hydrochloric acid?
Well, not for our lab purposes.
Not for almost anybody's lab purposes. There'd be very few situations where that would make any sense whatsoever, simply because logistically it'd be difficult because nobody wants a room filled with hydrochloric acid. Okay, so great. So you would pick hydrochloric acid to be aqueous in almost every situation as a reactant, just for ease of use. But when hydrochloric acid is made, what state is it going to be in? When water molecules are made in a chemical reaction, what state are they?
Aqueous then?
Well,
Oh,
water
okay.
can never be aqueous.
No, I misinterpreted what you were saying. So you're saying when we make water.
What state is it in?
We're starting out with gas.
I don't know, it doesn't matter. I don't care what you have. If you make water, what state is it in? It's a gas. Always. If you wait, it'll turn into a liquid. You might have to wait a half a second, or you might have to wait 20 minutes. So when we're making hydrochloric acid, what state is it going to be in? It's going to be in a gas. I could put it in water and make it aqueous, but when it's created, it's a gas. So why didn't we use the gas in this reaction?
Because it wasn't the.
Because logistically, it doesn't make any sense. So as a reactant, you're almost always just going to use it as aqueous. And then as a product, you just made it. I mean, it was just created in the universe. It's a brand new substance that was just made. So is it aqueous yet? No, it's not aqueous yet. It could be aqueous, depending on the situation, but when it was created, it was a gas. So the zinc chloride is aqueous because the chlorides are aqueous in water, and we know water is present because hydrochloric acid came aqueous, so I already had water there. And I need, what do I need? A 2 in front of the hydrochloric acid? That's it? Okay, so we got a balance. So I got 43 grams of the HCl and 43 grams of zinc and 75 grams of the HCl. What's going to be in the container? All right, so, okay. So how do I approach this? What do I do?
43 grams of zinc.
Sure. We just throw in 43 grams of zinc right here. And then for every 1 mole of zinc, what do I have here? $65.39. Okay. And so it's going to be zinc down here. And what, doesn't matter. What do you want to do? Okay. So we'll go to hydrogen gas. And so for every 1 mole of hydrogen gas, I've got 1 mole of zinc. So it's just a 1-to-1 ratio. And so for every 1 mole of hydrogen gas, it's 2.0159 grams of hydrogen gas. And so that'll be grams of hydrogen gas. Somebody punch that out. 1 point something or other. That sounds good. So what was the assumption that was made with this calculation? That you had enough hydrochloric acid. So now we're going to do the next reaction where we assume we have enough zinc and then determine which one of those statements was actually true. So I'm going to do 75 grams of HCl, and then for every 1 mole of HCl, it's grams of HCl. So what is that? Um, 35.453 plus 1.00795 equals 795. No, it's 9. It's, oh yeah, it is 795, but I didn't type that in. Okay, so I've got 36.461, and the ratio. So I've got hydrochloric acid down here, and I'm going to go. What am I going to go to up top? Why does it have to be hydrogen gas?
Because that's what we did with the zinc.
That's what I did with the zinc. So I'm trying to compare which one of those things is the limiting reagent. And so I need to go to the same thing to determine which one is a smaller number. So I cannot put zinc chloride here unless my first reaction I did zinc chloride. So for every 2 moles of the hydrochloric acid, it's 1 mole of the hydrogen, and then it's 2.0159 hydrogen gas, and 1, and hydrogen gas. Okay, and so now I've got 75 divided by my 36 divided by 2 times 2.0159. And so here I get 2.07 grams. Okay, so what's my limiting reagent? Zinc. So the zinc is going to be fully reacted. It's going to be giving its electrons away, and we'll have some leftover hydrochloric acid. So what I know right now is I've got this much hydrogen gas in the container. And what else do I know?
0 zinc.
I got 0 grams of zinc. So 0 grams of zinc. Alrighty. What do you want to do next?
Do the zinc and the zinc chloride.
Okay, so we'll do 43 grams of zinc. And for every 1 mole of zinc, it's 65.39 grams of zinc. And for every 1 mole of zinc, it's 1 mole of zinc chloride. For every 1 mole of zinc chloride, it's 65.39 plus 35.453 times 2. So this is 136.296 zinc chloride. And this is grams of zinc chloride. Alrighty, so that number times 43 divided by 65.39. I get 89.6. So I know that's how much of that I've got. I got this much zinc chloride. So you could do one of two things. You could do a 4th railroad track to determine how much of the hydrochloric acid was used, or you could simply say what? You could do some subtraction. So I know I've got 43 grams, and I've got 75 grams. So I've got 118 grams of reactant. That's how much stuff went into the container, so I have to have that much stuff when I'm finished. And I know 1.33 of it is hydrogen gas, and I know 89.6 of it is zinc chloride. So whatever this number is tells me how much of the hydrochloric acid I have left over. So 118 minus 1.3, looks like minus 90. So 26.7 grams of hydrochloric acid left over. That's what we have in the container.
I have a question
Sure.
about the sig figs.
Yeah.
Do we have to do those right from the get-go? Like when you came out with 75 grams of the hydrochloric acid for the hydrogen 2.07, should we have like just 2 sig figs there, or do we wait till the end?
Wait till the end.
Okay.
Yeah.
So it'd be 27 grams.
Sure. The problem with that is we're gonna have, the numbers aren't gonna work out because I've got a decimal place. So you're gonna need 3 simply because it's there. Remember the way it worked with addition and subtraction? You line them up, and whichever was the least, that's where you chopped it off. So we'll have, when you do the subtraction, you'll have a decimal place. Does that make sense? No?
So did that become okay because your equation made 3 significance when you added them together? Your
Uh,
118?
How about this?
Good question.
I pondered on that one, so.
Oh, I see what your question is. Because of the 118, is that okay? I see.
So did that change when you're gonna say what's left over?
But shouldn't it only be 2?
It's only, it's only 2, really.
Okay.
So
So we were correct in that, rounding up then?
that's fine, yeah.
Okay.
You only have 2 out of this.
I don't want to miss a point on the test.
Okay. You also don't want to kill somebody
Yeah.
later on when you're a nurse because of that. It might not seem like a big deal, but I don't know, maybe you work in the NICU, and then all of a sudden 1/10 of a gram or 1/10 of a milligram actually does make a difference, because we're only talking about something that weighs a pound. Okay, last question?
It turns into liquid at room temperature.
You want to say that again?
It turns into liquid at room temperature.
Nope.
Once we regards.
It wants to turn into a gas. The term volatile in chemistry refers to a substance's ability to turn into a gas. The more volatile you are, the more likely you are to turn into a gas. That's it.